Thank you, Yuri. Um, as you heard, I'm a theoretical physicist by training, and it's a little bit weird and strange that I'm up here talking about social science and cities. So I thought I'd just take a minute to give you the personal story about how that came to be. And as you heard, I got introduced to the energy problem in about 2004 when I moved to BP. And spent 5 years in BP and then another 2.5 years in the US government working to change the energy system by inventing new technologies. And what you understand, what I came to understand, somewhat to my disappointment, is that technology is only one lever and is probably among the more feeble levers that we have to change the energy system rapidly. What really governs the pace at which energy changes are societal factors: regulation, economics, behavior, perception. And as I was leaving the government in late 2011, so about 3 years ago, I said, I'm going to go work on those because that seemed to be the long pole in the tent. And somewhat to my horror as a physicist, I realized I was talking about social science. And so what was I going to contribute to that? After all, people had been working in those fields for centuries, as you all know. After thinking about it a bit, I realized it was the data, that we now have the ability to measure, instrument, understand what's going on in society with unprecedented qualities of resolution, coverage, timeliness, et cetera. And so I thought I'd go off and do data-driven energy policy. And you realize you should be doing that in the cities because that's where the people are. And then you realize that it's not just about energy in a city, but it's about everything that goes on: mobility, communications, public services, education, health, and so on. And so in early 2012, I started talking to a number of universities about going out and instrumenting a city. And various circumstances, NYU turned out to be exactly the place to be, and so I find myself now over the last 2 years working to build the Center for Urban Science and Progress. And as you will see, again somewhat to my surprise, not only do the social sciences help us understand cities, but the cities, I think, have the potential to provide insight into human behavior. And so in some sense, what I'm about to tell you is as much a request for help from those of you who understand the social sciences, and to try to give you a sense of what we see as the potential for doing social science with large urban data sets. Right. So let me just say a little bit about CUSP, and then we'll get into the substance. We're a unit within NYU, and we were announced in April 2012. I had the good sense to stand in the back on the right and let the dignitaries take over because, frankly, we had no idea what we were doing at the time. And it's become clearer over the last couple of years. We're a partnership. We're a unit within NYU. I report to the provost. We have a number of university partners, a number of industrial partners, not only several big data companies like IBM, Microsoft, and Xerox, but also Con Ed and National Grid, who provide electricity and natural gas to the city. The national laboratories, which are unprecedented resources for data handling, sensors, and computational modeling. And importantly, we're a partnership with city and state agencies concerned with New York City. 13 of the city agencies that range from health, buildings, environment, police, fire, the MTA, and the Port Authority. The vision is that New York City is a living laboratory, and we are about data for the city. We're about the acquisition, integration, analysis, modeling of all manner of data about New York City in order to help the city be better, develop new methods, new technologies. I asked myself now several years ago, what does it mean to instrument a city? As a scientist, here's an object I want to study. How do I go about asking what is I want to know about the city? And you come to realize it's really in 3 buckets. You want to know about the infrastructure, the roads, the buildings, the grid, the pipelines. What condition is it in? How is it operating? You want to know about the environment, not only the meteorology, pollution, but noise is really important in the city for many of us. And then finally, you want to know, most interestingly but problematically, about the people. If you take away the issue of privacy, you'd like to know location, interactions, economic activity, nutrition, health, etc. You can make a long list. Come back to privacy in a bit. And the underlying premise of what we're trying to do is that if we can properly acquire, integrate, and analyze this data, we can make the government better in terms of planning, efficient operations, and better policy. We can improve the engagement of people with their government. We can enable the private sector, including retail, insurance, political campaigns, all of whom want to know about the city, to develop new methods, new products and services. And most importantly for this discussion, we think we can bring new tools to the social sciences. There is a host of practical things that we're doing in the center, and this is just a list. I'm not going to say any more about these, but just to give you a flavor of the kind of things that we're doing with big data for the city, mapping the economy at the street level, helping the MTA optimize the number of bus drivers that they need every day, helping NYPD analyze events that they have to deal with. Attendance in parks is of great interest. How many people use a park? What do they do there? Yeah, I'm sorry. That was a rhetorical question, right? How many people use Central Park every day? They don't really know, right? And we have ways we think of helping with that. And so on, all right? These are all practical things. But I want to concentrate mostly on the science and ask what science problems are ripe as we go about looking at a city. The infrastructure and the environmental parts are pretty well understood, at least in principle. After all, they are built, they're designed, and we need to have the understanding to design them. And the interesting challenges there are really engineering. How do you make it work better, rather than basic science, looking at fundamental laws of physics or human behavior? But the human dimensions are intrinsic to cities, and they are among the least well understood. You can't study cities without studying people. The cities are built by people, they're used by people, they're there. They're where the diversity of human behavior and interaction is best displayed. We have concentrated, as opposed to rural areas, have concentrated behaviors and variety in space and time. We have people interacting with the infrastructure, and we think it's ripest for doing science. And it really goes both ways. The social science informs our understanding of cities, and conversely, data we have about the cities can help, we think, in understanding social science. So let me try to put it in context, my naive understanding of how social scientists do their business. We can do laboratory experiments of order 10, astronomical precision, of order 10 subjects at a time. We have invasive things like fMRI to get down at the neural level. And then we've got psychology tests like the famous marshmallow test, where you can study how people will. Intertemporal choice, I've learned, is the buzzwords for that one, right? We can do surveys, and I put down 10 to the fourth as a reasonable number for surveys, maybe relatively large. For academic surveys, it's probably more like a couple thousand. And then you can just watch. And I'll show you examples where we can deal with 1 million people at once just by watching, whether it's a city scene in the large, like that skyline of Manhattan, or a street scene like the intersections shown there, both of which, by the way, come from our offices in Brooklyn. The great sage Yogi really understood it all. You can observe a lot just by watching, and a lot of what we're doing is passive data acquisition and analysis of what goes on in the city. There's a long history to this of watching cities, and there's a lovely quote from a book by Patrick Geddes, who wrote, he was a British evolutionary biologist in the late 19th and early 20th century, who started thinking about cities as organisms, and naturally enough wrote a book called Cities in Evolution. And he's got this quote, which I'll just read through because it's so lovely and relevant to what we're doing today. Aristotle urged that our view be truly synoptic, a word which had not then become abstract, but was vividly concrete, as its makeup shows. A seeing of the city, and this as a whole, like Athens from its Acropolis, like city and Acropolis together, the real Athens, from Lycabettos and from Piraeus, from hilltop and from sea. Large views in the abstract, Aristotle knew, and thus compressively said, depend upon large views in the concrete. And so Aristotle had this view of seeing with high granularity, standing on the Acropolis, for example, looking down at Athens and trying to understand how the city worked. We can fast forward a couple of millennia and look at the work of Holly White, who worked in this city from the late 60s through the 80s. And he was both a journalist and a sociologist, mentor of Jane Jacobs, for those of you who know that name. And what he did, he was concerned with the plazas in New York City and set up a number of 8mm cameras. There he is on the roof with the cameras, watching how people used the open space in the plazas. How did they move around as the shadows changed? How did they group together as they interacted with one another? How did they use the street furniture and so on? Eventually wrote a book called The Social Life of Small Urban Spaces, and was very influential in helping this city become the kind of city it is today. The renovation of Bryant Park in the 70s was very much a product of his thinking. So let's talk a little bit about urban data. What are the sources that we have? Urban data have been collected for millennia. The word statistics comes from the German and ultimately the Latin word meaning of the state. And of course the Romans needed to understand what was going on in the cities of their empire, and so invented statistics as a way of understanding cities. However, if you go up to today as a scientist, you're struck by how little data have really been used to understand cities, making it difficult to usefully measure what goes on in a city. But we have new technologies now, which I'm about to show you some, that completely recast the study of cities. We've got digital records, we've got sensors, we've got computing power and analytical techniques to deal with that data and try to extract information from it with unprecedented granularity, variety, coverage, and timeliness. In many ways, it's like when Galileo turned a telescope on the heavens, or Van Leeuwenhoek first looked at a living cell. It completely changes the way we can look at cities. For what I'm about to show you, it's also unabashedly quantitative. Lord Kelvin, in the late 19th century, said that when you can measure what you're talking about and express it in numbers, you know something. And if you don't, your knowledge is of a meager and unsatisfactory kind. And so the approach I'll take is unabashedly that of a physicist or a physical scientist. I know that there are other traditions in the social sciences, and one of the interesting challenges is to learn how to mold those two ways of understanding social phenomena. So let me give you an example of what we've got. This is a diagram. It's about a year and a half old now. It is a city database called DataBridge. It was assembled in the last years of the Bloomberg administration and still is being populated today. And look at all the data feeds that you have, just starting from the upper left: Department of Transportation, Fire Department, Department of Finance, Sanitation, Housing, et cetera, et cetera. This is populated, and in the center that we're running, we have access to this data. The city, by and large, doesn't do much with it because, in fact, they're up to their rears in just day-to-day operations. But there's a tremendous amount of analytics that can and is starting to be done with this data. Give you an example. Again, this is not people quite, but it gives you a sense of the kind of things you can do with the data. Building energy efficiency. You can look at the energy use intensity of buildings. This is a histogram of about 1,100 buildings in New York City. How much energy do they use per square foot per year? And you can see that the horizontal axis runs a range of about a factor of 5 or 6. Some buildings use 6 times as much energy per square foot as other office buildings in the city. If you do the same for residential buildings, it's more nicely unimodal distribution, but still there's about a factor of 2 or even 3 swing in the energy intensity. Having enough data, you can start to focus in on the outliers and ask, is it the building construction, is it the operation, is it what they're doing in the building, or just plain old misreporting? You can then get a bit more social and ask, where is the greatest energy use in residential buildings per square foot, and this is a map that shows that. Again, I don't want to go into detail, but just to give you a sense of the kind of granularity that you can have in this data. This is an interesting graph, again, not people. We'll get to the people in a second, but it shows the energy use per square foot as a function of the year in which the building is built. And if you focus in on that light blue line in the middle, you can see that the old buildings use a lot less energy per square foot than the newer buildings. And that's because thick walls are a lot better energy-wise than the modern glass curtain walls. It's somewhat surprising. And then one more, this starts to now get at social issues. This is, again, look at the granularity, the fraction of household income that's spent on energy around the city. And you can see that the energy poverty areas sort of jump out at you. No, this is just building household energy, right? Yeah. Actually, transportation energy in New York isn't that much. People take public transport, most everybody, and yeah. Sorry? I have no idea. That's a good question. All right, different kind of data. Now, again, sensing the city. Taxis are a favorite of ours. They're a wonderful sensor of economic activity, human behavior, mobility patterns. There are 13,000 yellow cabs in the city, and they make about 500,000 trips a day, so 180 million trips a year. And with some foresight, probably about 5 years ago, the Taxi and Limousine Commission mandated that every taxi record for every ride the location of the start and stop of the trip, the time, the fare, the tip, the driver, the medallion number, and so on. And so we have, and we being Claudio Silva and Juliana Ferrer, who are two Poly and NYU faculty working in the center, we have data on 800 million trips for over 4 or 5 years. And you can ask lots of interesting questions. How does the tip depend on the weather, on the neighborhood? If you wind up in a rich neighborhood, is the tip proportionately bigger or smaller? That's interesting. How do drivers respond to a road closure? How do they learn a new route? And then more operational things like average travel time and et cetera, et cetera. This graph, which we'll come back to in a while, is a very simple analysis of the data. It shows for 2 years just the number of rides per day for each day in the year, 2011 and 2012. And of course, they're offset just because the day is offset from one year to the next. And what jumps out at you, first of all, is the weekly cycle. There's a high on Friday and there's a low on Sunday, average about 500,000, as I promised. You can see stuff happen, right? So you can see vacations setting in August, and then bang, over here, that was Hurricane Irene in 2011. You can see Christmas, pretty reproducible. That was Sandy. That was a half marathon running in the city. So this is pulse of the city, one of the regular repeating patterns which measure, in some sense, urban physiology, as well as containing details of behavior and operations. You can get more granular. Again, just an example of analysis. You can take 1 week in May, 3.5 million trips, and you can segregate out trips that come from the train stations versus trips that come from the airports, and look at it with very high temporal resolution. The upper graph showing the number of trips. There are more trips that come from the train stations than from the airports, with a fairly regular repeating pattern every day. But there are more tips shown in the lower panel that come from the airports compared to the train stations. Again, probably the cabbies know this intuitively, but it's good to see it played out, and again, get a sense of the pulse or the rhythm of the city. One last one on taxis, and then we'll move on. This is origin of trips in Manhattan over Sandy. And you can see the city functioning pretty normally on a Sunday. The storm hit on Sunday night, Monday. Everything got clobbered, and then the gradual recovery of the system over the next couple days. So taxis, big data, an interesting insight into what's going on in the city. We can get down at a more individual level. I'll show you an example, not from our work, but from a group at MIT and Stanford. They obtained from the phone company 500,000 CDRs, call detail records, which basically say at any given time what cell tower is a phone talking to. They got 500,000 of these for 6 weeks in the Bay Area and in Boston. And this is an analysis of some of the data in the Bay Area. And what it shows, this is for the morning commute. If you look at that road, East Hamilton Ave in San Jose, it is fed by commuters from 51 different cell tower areas. Whereas if you look at the road in the upper left, Hickey Boulevard in Daly City, it's fed by only 12. Using this kind of information, you can get what's called the origin-destination matrix, who's going from where to where during the morning commute. The way in which you usually get that is by doing a survey, a couple thousand people every few years. We've got 500,000 for 6 weeks, and if you run the roads or you're responsible for planning the roads, this is invaluable information. You can do even more. Now we get down to the individual behavior. By analyzing daily commute patterns, Marta Gonzalez at MIT and her colleagues were able to compare a survey taken in Chicago and Paris, phone data in Paris for 40,000 phones, and a model that they built. And they analyze the daily commutes and break it up into different motifs. So the first one on the left is just don't go anywhere. The second one is a bipolar commute, home to work and back. The third set are tri-commutes, et cetera, et cetera. And the proportion of people executing these different patterns over the course of some number of weeks is shown in the graph, and there's a model and so on. You can compare the data with the survey and et cetera, et cetera. So you can start to get this granular view of how people are living their daily lives. We're involved at NYU. We've struck up a rich collaboration with the new Institute for Interdisciplinary Decision Making. This is Paul Glimcher, Liz Phelps, and others. And we've come to realize that you can learn a lot, we think, from these data sets about how people make decisions. This is an example of analysis of lottery sales. You can get the lottery sales outlet by outlet in the city with 15-minute resolution. And what it shows is the areas where the lottery sales are the highest, not surprisingly the most economically impoverished areas. But then you can start to do things like correlating sales with the weather, with sports team performance. Lottery sales go up when the teams win. People are feeling more optimistic. With mood, we think, as extracted from tweets. You can go on and on. And the lower graph just shows you a temporal trace over some number of days of lottery sales. I'll show you a different way of looking at the city, which is inspired by this picture, which I pulled off the web now almost 3 years ago. It shows the view looking south from the Empire State Building, and you can learn several things from this picture, at least that jumped out at me when I saw it. The first is you can see a long way. I don't know the exact distance to the Verrazano Bridge, but it's probably 5 or 6 miles at least from the Empire State Building. The second thing that jumps out at you is there are a lot of lights. There are probably 50,000 lights in this picture. And the third thing that jumps out at you is that almost all those lights are not moving. The traffic that you can see in the streets around the Flatiron Building, not far from here, is of course moving. But most of the building lights, of course, the building lights don't move at all. And so having spent 30 years of my career at an institution, Caltech, which is preeminent in astronomy, I immediately thought, hey, this looks like stars. Can we do astronomy? And the lights go on and off. Can we understand that? Can we see them change color, flicker, et cetera, et cetera? The answer is yes, as I'll show you in a moment. But before I do that, it's worth understanding that there are, like astronomers, there are other ways of seeing besides the visible spectrum. This is an infrared spectrum of a city view. And so we're looking at heat rather than light. And for example, looking at that building, you can read the thermostat setting of every apartment in the building. That building, we know, has a data center in it. And so it's hot on the bottom and it's hot on the top where the vents are, and otherwise cool in the middle. And that set of buildings are the Alfred E. Smith public housing buildings, and you can see that they're glowing red because in typical New York manner, the heat is turned up and everybody's got the windows open to keep the temperature cool, right? If you're a physicist, you realize, hey, we don't have to do it just with heat. You can do what's called hyperspectral. I'll show you a little bit of that. You can do radar, LIDAR, and so on. What's interesting about this is that it's non-invasive. You don't have to go put a sensor out. It's granular. You can see with high resolution. It is persistent. You can just sit and watch. And it's non-permissive. You don't have to ask anybody's permission to do this. Needless to say, there are privacy issues, and I'll show you that in a second. But it's a very interesting way of capturing a lot of data at once and using it to infer things about how people are behaving. We've taken this into a serious concept. We call it the Urban Observatory, where you can take data from satellites, from aerial, rooftops, sea level, street level, organic data in the system, and execute this kind of persistent synoptic, we used that word even before we knew Aristotle used it, and granular acquisition of data about the natural systems, the constructed systems, and the human systems in the city. So let me show you some data and what we're doing. Here's of course, a view you all will recognize. That's the vertical overhead view. We're located in Metrotech in downtown Brooklyn, northern Brooklyn. And the view shown in that cone is shown on the picture on the right. Empire State Building, just about 3.8 miles away. Chrysler Building 157, that big ugly building that's going up. UN, et cetera, et cetera. If you look south, you can see Brooklyn from our view. It's a much flatter landscape, but a lot of people, 2.6 million people. If you look from Governor's Island at the financial district, you can see that. And if you look from Jersey, you can see that, all right? And so the challenge is to observe what's going on in these views with persistence and quantitatively. We call it the City Lights Project. We can learn about energy use. We can learn about sleep-wake cycles. We can learn about occupancy and behavior. To get into technical details a little bit, we took an 8.8 megapixel USB camera. We took one frame every 10 seconds for weeks, and then analyzed the data in a custom processing pipeline. You got to make sure the frames are registered right. You got to pick out the windows, et cetera, et cetera. Privacy, real important. We have built privacy in from the beginning in everything we're doing. There's an IRB at NYU, and we went to them, and they said, in part, why are you even bothering us? You're just looking at lights, and everybody in New York does that. But in fact, we have a chief data officer who's a privacy professional, a lawyer, Lynn Goldstein, who keeps us on the right side of privacy issues. We agreed that we would put a limited number of pixels on each window, and the nearest windows look like that, so you can't see anything other than the intensity of the light and the color of the light. And we do analysis in aggregate and de-identified only. So here's a video that shows you one day with the lights. This is the view. It's residential in the foreground and commercial in the background. This is early morning, so the lights are kind of quiet, not much is going on. We will see dawn break in a moment. There we go. You can see various bits of activity. We'll come back to that in a moment. This is basically William White on steroids, all right? Okay. And we can do a lot of that. I'll let it go on. So, late afternoon, there's a sun glint over there. Now dusk and the lights come on, and again watch the patterns in the residential and commercial. All right. So we can take each one of the windows in that scene, and we segregated out 4,000 of them in this first cut, And you can look at the intensity of the light in each window. This is one window, I have no idea which one it is, from 7 p.m. to 5 a.m. in the morning, and you can see transitions happen. Right? It's pretty clear that something happened just after 11 o'clock at night. Looks like the lights got turned out and went to bed, and then something else happened around 11:30, 12 o'clock. You can make up a story, right? The baby got up, or who knows what. All right? And you can identify, we've gone through and identified kind of the big off transition every night in every window. When does it look like somebody went to sleep? And then you can sort of make a picture for 3 weeks worth of data. The upper orange graphs show when the off times happen, and the lower blue graphs show when the on times happen. And you can see that there's some regularity to this pattern, but it also changes from weekdays to weekends and so on. And one of the interesting things we found is that if you just take one Monday and just order the lights in the time at which it looks like they went to bed, the big off time happened, you get this regular curve. If you use the same ordering but plot the Tuesday off times, it becomes quite random. But then if you use the Tuesday ordering for the Tuesday data, it comes back again. And so what we think we have found is that the aggregate behavior is quite regular from Monday to Tuesday, but the individual behavior is quite random. And in fact, if you look at the correlation function of an individual light, ask if it turned off at 9 o'clock on one night, did it turn off at 9 o'clock again the second night, or was it 10 or 8 and so on? And you can see that there's some spread by a couple hours, day by day. That big spike at 0, by the way, are the timers. They all go off at exactly the same time every day, and so you can conclude that a couple percent of the lights are on timers. You can only do this with the kind of granularity that a modern CCD enables. And of course, when you go back to the scene, I guess I don't have it, we have an ID on every building. So we can start to stratify this data according to demographics, building use, et cetera, et cetera. That's work still to be done, but we will do it. Let me just show you one cute thing. It's not about people, but it's about the environment in the city. We started to look at the images in daytime, and this is 3 successive images over 1 minute in some day, I don't know which day it was. Doesn't look like there's much different from one image to the next. They're roughly 20 seconds apart. But if you look at them carefully, you can see subtle variations, and I'll just flip through it. This is the first image, there's the second, and there's the third. Anybody see anything? No? I mean, that happens, but if you look in the middle, there's this big black thing that comes up in the middle. See it? There? Look just above the middle there. I'll go through it once more. So there is the first frame, the second frame, and the third frame, right? And so you can analyze that as we've done. Let me go back. I think this is the movie. Here's the animation. Sorry. So that's I think we're looping the animation. There it goes. See? Yeah. So what happened was somebody fired up the boiler, and this big black cloud of soot comes out, and we caught it. Right? You can see that a little more clearly if you subtract one image from the next and just look at the differences, which is shown in the bottom. You can see that big white blob of stuff coming out, right? And we colored it in the upper one so you can see it. I think we colored it red. Maybe we didn't. Anyway, there it is. All right? So we've got an interesting way of watching. There are probably about 800 buildings in this scene. We can watch every one and learn when they fire up their boilers, where does the pollution go, et cetera, et cetera. Nothing to do with behavior per se, but another way of watching the city. One more, and then I'll get on to some other behavioral things. You can take what's called a hyperspectral image, which is a picture not in 3 colors, but in 3,000 different colors, so that you have a whole spectrum for each pixel rather than just 3 RGB colors. And you can pick out selected pixels in this scene. There's one. We picked out that one, and it looks like what a physicist would call a black body spectrum, which is characteristic of an incandescent bulb. That one looks completely different and is in fact characteristic of a lower temperature incandescent bulb. And then that one looks really weird, and that's because it's an LED that has particular spectral lines in it. Again, if you're a physicist, you sort of understand this stuff. And so you can get a sense of the penetration of different lighting technologies across the city by watching. All right. As we talked with the neuroeconomists, we started to get interested in the notion of, can you do laboratory experiments au naturel in the wild? And we came up with this, again, we being Paul Grimsher, Michael Grubb, Masoud Gandahari, Greg Dobla, and some other folks. Can we do in the wild the analog of some classic lab experiments? And one of the classic lab experiments is an attention experiment or reaction time, where your reaction time is measured as a function of distraction, and it of course goes up as you get more and more distractors in the picture. So this is a street scene, and you can see there's a stoplight, people waiting at the light, waiting to jump off. And what we did was to pick out the two stoplights over here, and it's easy enough to analyze the video to understand when the light changes. And then you can pick out the guy in the box waiting at the light. And then you can do this, of course, ad nauseum during the day. And this is a set of light transitions. Red and green indicate the light turning red or green. And then you can analyze for each of those transitions. Here the transition happens. This is when the vehicle starts to move. And you can do the analog of the laboratory experiment as a function of distraction in the scene. How long does it take for the vehicle to jump off from the red light? No results yet, but there's data collection underway and beginning to be analyzed. There are other experiments that you can imagine like this, right? If you put a camera on a bus queue, you can ask how long are people willing to wait in the bus queue for the bus to arrive, and start to get at behavioral parameters. Of course, there are lots of cities and lots of lights, and you can imagine doing this kind of thing all over the world. Another one we're doing, quantified community, which is meant to understand the patterns of urban life. We are working with the Related company, which is a big developer here in New York City, which is developing Hudson Yards. And there will be about 10,000 people living in Hudson Yards when it's completely built up over the next 5 years. And we're looking to put an informatics overlay, sensing, data analysis, modeling on top of the whole development. Not just the building and operation, but also the people. To give you a sense of the kind of things we're looking at, obviously the analysis of the buildings, indoor air quality, resource consumption, the infrastructure, waste, stormwater, safety and security, the environment, but then also the people, behavior, mobility, and so on. How you convince people to live in this kind of environment? Well, if you got a break on your rent, you might be willing to do it. As you probably know, there's a whole quantified self movement out there, and we can exploit that sense of people wanting to know as well. Of course, there are ways to deal with the privacy issue and make sure it's done anonymously. So now let me turn, having done all that, what are some of the science questions associated with the city? And I've mentioned several times already this pulse of the city notion. The city happens every day. On the left are the taxis, on the right are the lights. Can we document the pulse in these various dimensions? What's normal? How variable is it from day to day? Are there correlations among the different variables as they fluctuate around the norm? How does it respond to perturbations? Is it predictable? Can we build something like a weather forecast model? The city happens every day. It should be repeatable, and we should be able to forecast the fluctuations around it. Can we see precursors of events in this physiology of the city? Remains to be seen, but it's an interesting thing to be thinking about scientifically. Second is a theme I've been talking about quite a bit over the last 30 minutes. Can large urban data sets teach us about individual behavior? Can we do these laboratory experiments in the wild? And then there is the micro-macro connection. The city is, in the large, is the manifestation of zillions of individual decisions. And how do the macroscopic properties of a city, the scaling laws that a group at Santa Fe have been looking at, the physical structure of cities, the decision rules that go into the models, what role does geography play, culture, politics, and so on, in forming the shape and large-scale structure of the city? That's a picture of Paris at night from a satellite and the lights. Right? Why is Paris that shape? Why is New York the shape it is? As we go through this, at least for a physical scientist, it is sobering to temper one's aspirations a little. We cannot approach the precision and rigor of the physical sciences just to show you what is in fact possible in the physical sciences. Quantum electrodynamics, which is the most precisely tested physical theory, is predictive at the part per trillion level, right? 1 in 10 to the 12th, and that's for some magnetic properties of the electron. Of course, that's a simple, reproducible, isolated system, but there's a simple but non-trivial theory with a small parameter in it, a small number, 1 over 137, and never mind where that comes from exactly. On the other hand, in the physical sciences, we're not wholly predictive of complicated systems. We see statistical behavior, chaos. Climate is a really good example, even weather, of the failure of predictability in a physical system. But I think we might be able to aspire to approach the rigor of the older earth sciences or biological sciences, where we can have frameworks or theories, for example, rational choice, macro statistical laws like supply and demand, probably good for trends at better than 10% significance, good for outliers, but tougher in between. The challenges that we face in trying to do this science, much of the data is observed rather than designed. You've seen a lot of that already. It's collected for other purposes. It's heterogeneous. It's got problems in quality, coverage, and bias. The data are in silos. This is a peculiar thing for urban data. The Department of Transportation may not want to share with the fire department, for example. And so you've got to go around and collect all this data, particularly if you want to go to private data like credit card information, for example. And you can't easily do experiments. On the other hand, natural experiments happen. There are weather, the president visits, and it messes things up. We can look at before and after differences in neighborhoods, different cultures, geography, and so on. You got to be careful, though, because of spurious correlations. I'll show you some example where we, in fact, understand a lot just by watching, and that's in stars. When people started looking at stars quantitatively in the late 19th century, they started to measure the color of the star, which is an indication of its temperature, versus how bright it was. And they made this plot, which is just a correlation between those two observables. It's got a very nice structure to it. This is called the Hertzsprung-Russell diagram. It basically shows the evolutionary tracks of stars. And it took about 30 or 40 years until somebody wrote down a physical theory, which actually very nicely describes this. So this started by just looking, but then a theory got overlaid on top of it, and we now understand this really quite well. Big data changed astronomy. In the early 1990s, astronomy underwent a transition from one observer looking for a couple nights in a big telescope at a couple of stars to a big data mode in which pictures were taken of the whole sky, and so you had one astronomer looking in a database at thousands of stars at once, and led to really interesting discoveries. This one I just pulled out is supernovae, which tell us about the cosmic expansion of the universe. It used to be that you were lucky if you had 3 supernova a year that you could study. They had names, supernova 1, 2, 3, and so on. And then suddenly we've got 500 supernova over 3 years from this big data way of doing things. And it has let us do science in astronomy that you just could not have done before. So the aspiration is to do something like this for social science. You got to be careful, though. You can always find spurious correlations. I love this one. the per capita consumption of cheese correlates with the number of people who died by getting tangled up in their bed sheets, right? So you got to be careful. You just can't go mindlessly prowling around big data sets. Privacy, big deal. Right? We need to develop methods, protocols, audits, technologies that let us extract information from data sets like this while preserving privacy. As you all know well as social scientists, the system that we're trying to study is reactive. And that means that when you learn things about it and people learn about what you've learned, they may well change their behavior. The stars, of course, don't have that problem. And we're discovering that the dialogue between those of us who are technical and geeks and the social scientists is not an easy one. There are different ways of understanding the world. One of the challenges we're facing in the center is to bridge this, but we think that there's a lot of gold to be had here if we can make this work right. We're serious about privacy. We sponsored a book that was published in June, Privacy, Big Data, and the Public Good. How do you in an academic organization deal with this intersection of data and privacy? It was edited by Julia Lane and Vicky Stodden and Stefan Bender, and the authors are a collection of lawyers, ethicists, and computer scientists, as well as, again, the interloping physicist over there to just try to give some rationale for why we're interested in this. Let me say a word about education and how do we educate people in this big data urban context. This is the second class that we have at CUSP. It's a master's program, 1 year. There are 64 students that started about 6 weeks ago. The first class was 23, and so we've grown by just about a factor of 3 in 1 year. A really interesting collection of people pursuing this 1-year master's degree. About half of them come from abroad, 19 countries. Almost half are women. They've been out on average 5 years from their bachelor's degree. A third of them have graduate degrees, and interestingly, 7 of them are current New York City employees. One of them is an active duty cop, and so it gives a very interesting flavor to the class and the kind of things that people are working on. Where did they come from? About a third of them have degrees in engineering, another fifth in science, and a fifth in social science. And I've highlighted some of the social science disciplines that are represented there. The goal here is to get a group of people who come from diverse backgrounds focused on cities. Not only the very practical things that we think we can do with big data in terms of city operations, but also some of the science that we think we can do as I've outlined here. I think, so I see I finished somewhat early, but we've got some time for questions, comments, and in particular, again, we're looking for social scientists who think that they can do something interesting with this data, so request for collaborators is certainly on the table. Thanks much for your attention, and we can get into some discussion and questions.